In this video, we're going to go over the idea of permutations now from the perspective of group theory. So previously, we were talking about functions, and in particular bijections. Now we're going to organize this information into a group. So given a set, which maybe we'll call it S for set, consider the collection of all self-bijections of S. In other words, we're saying the set of all functions f s to s, f is a bijection. And the operation is function composition. What we're going to do now is explain why this gives a group. So let's remember what we need to do to see that something is a group. We need the operation to be associative. We need closure under the operation. We need every element to have, or sorry, first we need a neutral element. And then once we have a neutral element, we can ask that every element have an inverse. And let's go and think through these properties. So first off, associative function composition being associative is one of those classic facts that we all know from our school days about, just working with functions. So we'll consider this guy just kind of done. For the closure, what I have to do is see that if I have two elements of G, maybe we call them F and then we call the other one G, that if F and G are individually permutations, so is F composed G. And this is basically just remembering the properties that we saw in the last batch of videos and also in the homework, that since F and G are both injective and surjective, their composition is both injective and surjective. And so therefore, G following F inherits those properties. So we're good. Maybe I should write down inherits these properties from F, G individually. For the neutral element is the identity function. X to X. In other words, for every element little x, sends it to itself. And people usually denote this by either the letter I or maybe E. Sometimes you see this with the number 1. Doesn't really matter how we notate it. In Pinter, they use this kind of epsilon looking thingy. We could use that notation. We can see that this is an identity because if I evaluate this on any particular x, that gets me f of x. And then this identity does nothing. So you get f of x. Similarly, if you have f composed with the identity of x, then this gets you, well, f of the identity. And the identity does nothing. So again, just f of x. So it's a two-sided neutral element as required. So we're happy. The last part is the presence of inverses. And this boils down to a function being bijection. So we learned that if you have any bijection x to some other set y, then there is some inverse y to x. And we talked at great length why bijectivity is required and how this function is constructed previously. So all we have to do here is just see that in the special case where y is equal to x, all those comments are still true. So whatever the function is, you think of this as some sort of self-rearrangement. F inverse just puts these guys back. So we're done. That makes this guy a group.